In today's lesson, we continue our knowledge of direct variation or proportion. In question 6, the graph on the right shows the cost of the hamburgers purchased from the local takeaway store depends directly on the number of burgers purchased. Let's copy the table below and use the graph above to complete it. So for the number of hamburgers, okay, 1, the cost of it, if you go from 1 on the horizontal axis, touching the red line, intersecting it and going across to the left-hand side for the costs, we can see that this is between 5 and 10. The average of 5 and 10 is going to be 7.5, which is $7.50. Now, for 2 burgers, it will be exactly 15. And you notice that this is the same thing as 2 times of $7.50 because it's that much for 1 burger. So if we do 3 times $7.50 now, we get $22.50, okay? And this is represented by this number here, which is in between 25 and 20. For question B, find the variation equation to represent the relationship between costs and the number of burgers. So we've got cost, which is C, burgers, which is H, and so C would equal to KH, basically. So in this case, we're going to substitute in just a pair of values. So I'll do that with the first pair. So the cost is $7.50 when H is 1. So that means K is just $7.50. Okay. So if we put that back into our equation here, C would equal to 7.5 H. So whatever H is multiplied by $7.50, and that'll give you your costs. So this makes it perfect for question C because it says here, if Kim buys 6 hamburgers, what is the total costs? So all we do is we put the number 6 here for 6 hamburgers. So 7.5 times 6. That will give us $45. Then for D, the total cost of 1 order of hamburgers is $82.50. How many hamburgers were ordered? So $82.50 refers to the costs. We've got to find H. So if we substitute in $82.50 to that, and then divide both sides by 7.5, $82.50 divided by 7.5 is going to be 11. So it takes 11 hamburgers to cost $82.50 in total. And whereas for question E, okay, question E says to find the gradient of the line. How is it related to the constant variation? The gradient of the line is very simple to find. If we analyze these 2 points on the line, which are on the corners of a square, we can see that the rise here is 15. Whereas the run here is 2. So your rise of a run, which is the gradient, is 15 over 2, which is 7.5. This is exactly the same thing as our value of K, which is the constant variation. Okay, so we can say here that the gradient is equal to the constant of variation. And not only that, what does 7.5 represent? This would represent the cost of each hamburger. Okay? So per hamburger, it will cost $7.50, basically. Right. Let's now move on to question 7. Just give me a second. Yep. Okay. 7. K varies directly with L. If L is 9.5 and K is 1045, what is the value of K when L is 1.65? Okay. So if K varies directly with L, usually you would write the constant variation here as K, but because there's a K here already, you want to use a different letter. So let's just say K equals to ML. Okay, where m is the constant of variation in this case. Then what we can do is we can substitute in L as 9.5 and K as 1045. So 9.5 equals to M, oh whoops, it's the other way around. K is 1045, sorry. And that's equal to M times 9.5, which is 9.5 M in this case. So if we divide 1045 by 9.5, we get 110. So therefore, putting this back into this equation, K would equal to 110 times L. And we're trying to find out the value of K when L is 1.65. So if L is 1.65, then what is K? Let's put it in our calculators and we get K as 181.5, which is the value for answer C. Right, question 8. A linear relationship exists between the mass of a car and its fuel consumption rate, FL per 100 kilometers. So consumption rate is always measured in liters per 100 kilometers. Okay, you can find that on any car website. Then a linear relationship just means that it's directly proportional to each other. So the heavier the car, the more fuel it uses. Find the variation equation for F, the fuel consumption rate, if a 1,000 kilogram car uses fuel at the rate of 6 liters per 100 kilometers. So the two numbers we're just going to be using is just this and this, but we're using those two numbers to find a variation equation for F. So F, the fuel consumption, is directly proportional to the mass of the car. So F equals Km. And we're now going to substitute in F as 6 liters, whereas M is 1,000 kilograms. So basically, if I divide 1,000 over, I get 6 over 1,000 as K, right? Which is 0.006. Then for question B, find the fuel consumption of a 2,500 kilogram car. Okay, so before we actually go into that, we should actually write down our final equation now for F. So F is equal to 0.006 M. And if we now substitute in M as 2,500, we get 15. So this means the car uses 15 liters per 100 kilometers. Question 9. For an object that is cooling, the drop in temperature varies directly with time. If the temperature drops 8 degrees in 5 minutes, how long would it take to drop 10 degrees Celsius? Okay, so in this situation, the longer we wait, the more it would drop, okay, over time. Okay, so let's look at the two quantities. They are temperature and time, right? So temperature is usually used with capital T. So capital T is directly proportional, which means we write K to little case t, okay, or small case t. Now, we've got to find K. So to find K, the temperature drops 8 degrees Celsius in 5 minutes. So capital T is going to be 8, whereas the lowercase t is 5. So 8 equals to K times 5. Now, if I then divide both sides by that 5, K would equal to 8 divided by 5, which is 1.6. And if I put that back into the equation, T would equal to 1.6 T of that. Now, we're trying to find out how long, which means we're finding the lowercase t. How long would it take to drop 10 degrees, which is our capital T? So 10 would equal to 1.6 t, like that. Now, if we divide by 1.6, this will cancel out. So t is 10 divided by 1.6, which is going to be 6.25 minutes. And that will be answer A. Question 10. The weight of an astronaut on Mars is proportional to his weight on Earth. So those are the two places. A 72 kilogram astronaut weighs 27.4 kilograms on Mars. Calculate how much a 60 kilogram astronaut weighs on Mars, correct to one decimal place. So for part A, we'll find out the equation first, where Mars is directly proportional to weight on Earth. Okay, so we're going to find out K now, and we do that by substituting something we know about Mars and Earth. So a 72 kilogram astronaut weighs 27.4 kilograms on Mars. So this represents the weight on Earth. So we're going to substitute that as 72, whereas on Mars it is 27.4. So by dividing by 72 on both sides, that will cancel out. So that K is equal to 27.4 divided by 72. Now, that gives you a very, very long decimal. It gives you something like this on the calculator. And we're not going to actually write that at all. We're going to write the fraction version, which is 137 over 360. If we put that back in our equation now, m would equal to 137 over 360 times E. And if we're trying to find out how much a 60 kilogram astronaut weighs on Mars, we're going to replace E by that number, 60. So multiplying my answer by 60 does give us M equals to 22.83. It has more numbers after that. But approximately what that equals to is 22.8 kilograms. Now for question B, if an astronaut weighs 32 kilograms on Mars, calculate his weight on Earth. So this time we're given M, we're trying to find out E. So 32 will now equal to 137 over 360 times E. There's invisible times in the middle there. But if we undo this, that means we're going to divide that over. So we're going to write 32 divided by 137 over 360 equals to E. So 32 divided by that fraction will give us E equals 84.087 ... So E would be approximately 84.1 kilograms. Okay, and that's the weight on Earth.